let's start. My name is Thomas Weible, co-founder and CTO at Flex Optics. We are mainly in the optical transmission, but we heard from Johan. More up? Here we go. All right. That the transmission part is also quite important when you have a massive load of data. And the topic we brought today is more a game changer, and we show later on what's happening now in optical transmission and where we think it's a game changer. It's about coherent modules and coherent transmission. We split that presentation in two parts. Gerhard is introducing himself. Later on he's doing the theory, and I'm doing or showing the technical example how we did the implementation with the coherent pluggables together with DKIX. So, give you a short intro where we are coming at the moment, or where we are at the moment when it comes to de facto standards in terms of transmission speeds and applications. It is about 100 gigabit currently, state of the art, what we do when you interconnect switches, routers, and also high performance computers. And there are some drawbacks. Those acronyms, the CFP and CFP2, these are form factors used to do or to enable the pluggable transceivers. And when we look at the CFP, for example, it was a great design in terms of we were able to put a lot of components in that pluggable module, but it had a huge drawback. It took a lot of power, and it was, in terms of size, it was really big. And when we compare them, there was some evolution with the smaller form factors, the CFP2 and CFP4. And the latest one, or the one which is mainly used, is now the QSFP28, which is a nice, tiny form factor. Having, again, a drawback, it cannot take that much power and cannot consume that much power. And when we want to connect long distance links, like 40 kilometers, 50, 60 kilometers, we need some power. And so this whole 100 gigabit ecosystem was mainly designed for inner data center links and within metro spans. Now, for longer links, DWDM, dense wavelength division multiplexing, is used still. And to enable this, a DSP is used, doing all the modulation there when it comes to coherent technology, but with the effect that it was a big chip and a big size of chip placed on a line card, comparing now with the current solutions doing 400 gigabit. We have now latest technologies doing really tiny structures on chips to 7 nanometers or even down to 5 nanometers. I'm aware there are other techniques around to do 3 or even 2 nanometers, but we are still in the telecommunication world and not in the AI chip and CPU and GPU world. So this is a big advantage now, having 7 nanometer structures, getting a small tiny DSP with a certain amount of power it consumes and the size. And those DSPs are now placed on a module doing 400 gigabit and enabling coherent transmission. So that's the current state, and I hand over to Gerhard. Oops, sorry.
Thank you very much, Thomas, and yeah, welcome. Oh, the light is hitting on me. Let me switch a little bit and talk about some theory about transceivers and coherent transceivers. Yay! Coherent light. Do we not already have that in transceivers? No, not quite. A transceiver could be an LED that just shoots light. With coherent transceivers, the speciality is that we want to detect more properties, but more on that. Talking about light, what we usually try to push are our bits, like you can describe it by step functions, but when you measure it in reality, what you see in your oscilloscope is something more like that, because nature, how it works, you always have a transition, obviously, through your values, so there are never these perfect jumps we want to have. And the thing is, this is an easy way to, really very simple way to describe how transceivers work. And if you want to increase the bandwidth, what you usually do is increase the frequency. Increase the frequency and you get faster and better. Like with the CPU in the 19s, more gigahertz, more power. But, of course, you're also hitting limits. And let me show what it is, because if we increase the frequency, like increasing the steps, and we want to detect for the photodiode our signal, we have to change our threshold. Now you see here, we have -1 and 1, so that is your threshold you could put and say, okay, this describes my 1 and my 0, whatever, and now I have to change it. I have to put it on 0. Okay, we are fine, we can do this, but we have a smaller margin of detection. And if we continue doing that, it becomes even smaller. Like, look here, we have a 0.75 of threshold, which represents for us a 0, and like 1, detecting that in an exact manner is quite difficult. And yeah, getting a little bit to, maybe you have heard of the eye diagram. What is the eye diagram? Usually when you have an oscilloscope and you have a frame that is moving with the signal and you are measuring the signal quality, what you end up seeing is sinus wave upwards and sinus wave downward at the same time. Just imagine you're folding it a little bit and you have like an O here, and this looks like an eye. And if the signal is not precise enough, you start to see odd odd points there and lines and so on. So that is one thing. The other thing is, I was talking about coherent light. I was talking about amplitude, right? 1 and 0, and where's the threshold to measure through the photodiode. Now, the light has more properties, and it's a little bit unfortunate that we have, we have been trying to discover that current transceivers isn't a technology that isn't that new, but what is new is that we have that small pluggable form factors where you can, with the proper DSP, with the current technology we have, 7 nanometers, really manufacture something like that. So what are the properties we want to look here? Let me start with polarization. It's quite simple. Polarization, I don't think I need to explain you what this really means, but to give a small example, which we usually come up with, who has a screen protector on his notebook? Who has it? Do you use it? Like you watch from an angle and you don't see a picture because you want to protect that others don't see it. So that's the idea, and we are reversing this a little bit, because if instead of a diode we use a laser that shoots coherent light, we can also rotate this laser. We can calibrate it a bit. So we just shoot the signal wave over a plane, but we have a second plane, because you have the z-axis, but you can also rotate it, and you have another sinus curve. So when you combine them, you can add them vectorically. What you get, or you could see it as a diagonal plane that is moving the whole time, and something you can configure yourself. But you can split it up into components, because we have 1 dimension for the axis and 2 dimensions left for the area of your transceiver, of your fiber cable. So basically we have 2 planes, and if you rotate the signal, this is now in combination with phase shift. I'll get into this in a couple of minutes. It looks a little bit like a sinus wave, but since we have phase shift, it doesn't look as such. But imagine we don't have phase shift, it would be more like a sinus wave. So this is a signal you, through a simulation we calculated, you would get when you are checking current transceivers. Now if I rotate it even more, you see it becomes a little bit volumetric, and what you're really seeing here is the signal of a coherent transceiver. It transports a lot of information, and polarization has advantage. Since I'm talking about 2 planes we can benefit from. Of course, you are doubling the bandwidth already. So by just using polarization, you already doubled your bandwidth. Yeah? But that is one thing. The next thing we are going to observe and improve, and that's something we also can do with the current transceiver, is phase shifting. Phase phase shifting, as you have seen it in Wi-Fi networks, can also be used when you transfer coherent light and measure it at the other side with a local oscillator and a mixer. So OOK is the most simple constellation. What I'm showing here is an imaginary component. It is also called Navier-Jarreau quadrature component. Then we have the in-phase component, which really is the real axis. And yeah, this is basically the center. So on off is another description of what I showed of a non-coherent transceiver. But now let's dig deeper and try different constellation. PAM4 is when you use different amplitudes. We are still not at the coherent part. But now we are making it more interesting. Now we have 16 combinations. And with 16 combinations for one frame, you're pushing way more data, way more bits. And that is the advantage you can achieve with coherent transceivers. Obviously, it requires a DSP, but that's the idea of it. No? Maybe getting a little bit back to a very simple kind of transceiver. Maybe, or I mean, it is related to some optical interaction you have here. We are defining one detector as the real part and the second as an imaginary part. But the question here is, I like to ask, why do you think we are doing that? Why do we have a rotary disk and why do we need the imaginary and real part? So we have this rotating disk that produces a signal of a given frequency. So sometimes it's covered, sometimes not, depending on the orientation of this disk. But the question I'm asking you, to your as an audience, why do you think we need two readers? What's the purpose of the second reader? I mean, it's imaginary, I get it? Yeah, the question already was answered, yeah. Any ideas what it could be? Okay. The thing is, if you have phase shifting and you look at the signal and imagine you're moving it, you can determine the direction. If you want to measure, for example, rotational speed, into what direction is rotating this disk, you cannot find out with just one reader. But if you get a second one and you check the pattern, which part is on one in real, and the imaginary part, when is it on one, and what kind of phase shifting we have, you can find this out. You can see in which direction this disk is spinning. So yeah, that's another example. And we are getting back to the 16 quant signal. I prepared a play of cards for you. And what I'm going to ask you in this small game is, you can see your cards on the table. I want to know who is transferring 1, 1, 1, 1. 1, 1, 1, 1. Yeah, right? So if you want to transfer that series of bits, we have to look for the point. What amplitude do you have to set up your current transceiver and what phase? Can you tell me that?
I'm the center of the diagram.
Ah, yeah, by the way, here's the center.
The middle.
So if you look on your table, which card is it? Any idea which amplitude and phase we have? Yep, that's it. So 45 degrees, where is it? Center is there? Right, yeah, got it. So that was for warm up a little bit. Now let's try with 0101. Where do we have it? A little bit tricky because I covered some numbers. It is here. So what angle do we have here? Yeah, right. Awesome. And last one. Last but not least, we like to say 0011. It's around here. Yeah. Thank you. So with that, I'm calculating this as packaged. The audience was very reliable, 0 error rate, because if we want to calculate the error rate, the photodetector system, photodetecting system I call it, doesn't mistake on that regard. The bit error rate goes high, right? And for that solution, yeah, we have a couple of solutions like forward error correction. That is something you can do. The audience doesn't need that. Perfect. Thank you very much. And getting to the next slide, signal quality is another way to measure it. That is the view of an electrical engineer, signal and so on. We like to use dB because, you know, it is based on decibel, logarithmic. Log A times B is the same as log A plus log B. And if you applying an amplification of signal, you can just add it. But the idea is really with signal to noise ratio, how much useful signal to have compared to the noise. That is here you don't want, because you always will have noise, right? Then ESNR and OSNR, yeah, there's a difference between electrical and optical, obviously. You have electrical connection to your transceiver. Optical is what goes out, the light, or current light. And to give you some examples how the 16-QAM constellation looks when we have a transceiver with some simulation I made, some statistical application based on the Gaussian curve, you know. If we have a good signal-to-noise ratio, which should be high, like the curve I showed you before, the constellation looks like this. So if you put here your guitar, your mesh, you can still clearly, as a photo-detecting system, find out to which bits it belongs. But the lower this SNR gets, well, it gets worse. Here you can still detect, but here you don't know. Maybe some of these spots was hit there, but it was meant to be transferring at this area. So 5 dB is not a good transception. You're getting closer to your noise, and that is what you want to avoid. Well, that's enough about theory. I hope I didn't bore you too much, but let's get to the practical part. Thank you very much.
Thank you very much, Gerhard. So what we did is we took a pluggable module, looks like here in the middle, and talked to DKIX in Frankfurt. They operate one of the biggest exchange around the globe. And the GSI and FAIR network is also connected to the DKIX. So when you're surfing the internet, you will most probably be transmitting on those modules. So we plugged it in their routers and looked at the command line interface, basically how the operating system is recognizing those modules, and especially which new parameters we're gonna see. So it was pretty simple. We were basically running a show port command on the Nokia operating system. DKIX is running Nokia gear. And there are basically 3 sections on that interface. The first one is more about the physics of the module, or the technical capabilities. And we see here it's a 400 gigabit module doing DWDM fully tunable from the start frequency of 191.3 terahertz. Actually it's shown in megahertz, but it's a huge number with a lot of zeros, so typically we talk in terahertz, to the max frequency of 196.1 terahertz, or way simpler, channel 13 up to channel 61, which is way easier to talk about. It's currently tuned to channel 23, and the nice thing about those Coherent modules as well is it's not only tunable, you can also select the grid in which we want to slice down our DWDM network, which is quite convenient, and we are not tied to a certain grid. Well-known grids are 100 gigahertz and 50 gigahertz. Yeah. The second section is about diagnostic values and diagnostic monitoring, and everyone who is operating these kind of components, those switches and routers, is really aware of doing a monitoring of those modules, and there are 5 well-known parameters. It's the voltage, it is the TX and RX power levels, and it's the bias power or current going through the laser. And one important one is now also the temperature. And why do I highlight the temperature? Because typically in the past the temperature was not so important to monitor. We were always in range. Now when we look at the figures, in optical transmission the math is quite simple. So we feed in a lot of power, and typically those tiny modules take 17, in some circumstances up to 20 watts, and we have not only one module in such a switch, we have 20, 30 on a small dense unit. And we convert it basically to heat. And the major electricity, the major watts are converted to heat, and only 0.001 watt is converted into a light level, which actually is 0 dBm, which is a really low level of light we get there. And therefore because we have heat, we have to monitor and take care about the temperature quite well, because otherwise we will overheat the whole thing. And the third section we saw there are now the coherent parameters, and they are quite new to the optical transmission world when it comes to the pluggable modules, and I will go through them now step by step. So the first one, what we saw there is the RX channel, and typically when you talk about a tunable transceiver, you think about the laser, the TX channel, which you tune. Now with coherent modules, you have also the capability, when the physics are able to do it, that's a really important note, you can also change the receiver channel if you want. And if you want, and why would you do that? You can do this, for example, if you want to do a single strand transmission, so instead of running 2 fibers, one for transmit and one for receive, you can do it on a single fiber, having 2 different frequencies on one fiber, basically. But to do so, you need a separate local oscillator inside, and not all modules does support this. Then the next one is about dispersion. We have basically 2 types of dispersion on an optical fiber. There are a lot of dispersion types, but for this type of transmission, it's about the change or the change of the velocity while the light is traversing on our fiber. We have the chromatic dispersion, and this will change the longer our span is. The great thing is we can compensate it now with the effect of the DSP. We can do the math and do calculations on it. This link we were operating was a span of 15 kilometers on a regular single mode fiber, a G652. And this has, when you look at the characteristic of such a fiber, it has roughly 10 picoseconds per nanometer per kilometer of the chromatic dispersion. And when we do the measurement, we got 220 picoseconds per nanometer. So when you do the reverse mathematics, you can even calculate your link span. This would end up in 22 kilometers, which is not true. We were running at 15 kilometers. So we weren't quite sure where this offset is coming from, because we did a back-to-back link with only 2 meters of cable, and then we saw there 80 picoseconds. So there was somehow an offset, maybe of some not proper calibrations. We were not quite sure where it was coming from, because the actual fiber was 15 kilometers. Beside the chromatic dispersion, as Gerhard mentioned, we have now 2 polarization planes, the X and Y plane, and also the velocity of the light between those 2 planes can differ now. And this is the different group delay, or also polarization mode dispersion. And we do this also measure in picoseconds. This link had a delay of 2 picoseconds, and we are able to compensate up to 10 picoseconds with the module, but not more. Moving on, OSNR is now really important to monitor, and we have again 2 OSNR levels. We have one on the X plane and on the Y plane for the 2 polarization directions. This link was running at 34 dB, which is perfectly fine. We can go up to 24, 26, depending on which standard we are following. And then the bit error rate will go really, really up, and we are having flapping links or even a broken link. And there's another value which is quite helpful, is the RXQ margin. Here it's running at 2.4 dB. This is basically the margin, our forward error correction, which is also part of the digital signal processor, where the forward error correction is still capable to correct errors. So when we eat up this margin down to 0 dB, then the forward error correction is not able to work within specification and provide a proper bit error rate. And yeah, this is in correlation also with the prefect error rate, which is 10 to the power of -3, which is perfectly fine. And this margin, when you have a really back-to-back link, only with a couple of meters, is roughly 4.5 dB. The great thing now with those modules, and also with the fact that we have the possibility of the DSP doing the modulation, doing the forward error correction, we can even modify now the way we want to operate it. So it's not a pure 400 gig module. It is somehow we can support a couple of applications doing, for example, 2 times 200 gigabit or 4 times 100 gigabit, or even some odd numbers like 1 times 300 gigabit. It's just to the fact how we do the setup of the DSP and how we want to operate it. And the drawback is currently, or what we have seen is, there are no checks. So, for example, this module is set up to a compatibility called OpenZR Plus, but actually it's not capable to do it, because when we look at the first section, it does only support 2 application modes. The first application mode 1 and 2, the first 2 top ones, and the configuration of the switch itself said, hey, I want to do another application mode, but actually it's not supported, so there are no checks in that operating system. And as I said, there are a couple of de facto standards or industry standards out there. There are 2 major ones. It's the OIF 400ZR, defining typical TX and RX power levels, but also now for the Coherent modules, the dispersion, the critical dispersion values about chromatic dispersion and the PMD, and the OSNR tolerance. And the second one, that's the one which is currently the most interesting one, because it's slightly newer, but it gives more flexibility, especially when we look at the OpenZR Plus standard doing the 60 high power HA, having a huge launch power of 0 dBm. And why is this so important and critical? With that, we don't need external amplification to boost up to 50, 60 kilometers. Which is quite handy and great. And also when you look at the chromatic dispersion, it's way more tolerant for longer distant links, and that's actually very, very handy. To sum this up, as I said at the beginning, the DSP inside of those modules is now kind of a game changer in optical transmission. And when we look at this graph, it's pretty much obvious. So the green dot here is typical pulse amplitude modulation, where we are currently, or what we can do. But just due to the fact with raw compute power, we are able to quadruple the amount of data on the same type of module. So coming from 400 gig, we can easily reach 1.6 terabit, for example, just of the fact using a different modulation scheme to dual polarization 16 QAM, for example. Another possibility is to increase the overall frequency, what also Gerhard showed at the beginning, but there are currently definitely limitations on the electrical substrates using for PCBs. We are already at 50 gigabaud, which is a really high frequency, and we can do in mass production 100 gigabaud, and that's also used now for 800 gig and 1.6 terabit. Brings me to the end, almost in time. Thank you very much for attention, and for sure we are around, and if there are questions or if you want to dig deeper into it, how to do the implementation, maybe on your equipment, we are more than interested on it. Thank you very much.